Hello, in today's lecture we will talk about basic circuit laws. By basic circuit laws we usually refer to three fundamental laws related to electrical engineering. These are Ohm's law, Kirchhoff's current law known as KCL, and Kirchhoff's voltage law known as KVL. These three are very important laws for solving electrical circuit problems. In this course, almost in every circuit that you solve, you will use one or more of these three laws. We start with Ohm's law. We earlier mentioned that in this course we will deal with 5 different types of circuit elements. However, Ohm's law applies only to resistance. Ohm's law is not applicable to any of the 4 other circuit elements. And Ohm's law says that in a resistance, the voltage across the resistance is proportional to its current. So if we have a resistance R, the voltage across the resistance is V and the current is I. According to Ohm's law, V is proportional to I, or V is equal to Ri. R, which is the proportionality constant, is the resistance here. You will note that when the reference of the current and the voltage are observed, we see that passive sign convention is satisfied. So V is equal to Ri is Ohm's law when passive sign convention is satisfied. If we reverse the direction of the current in the same resistance, in the opposite direction, the current we can call I prime. Now we cannot say that V is equal to Ri prime. Instead, we have to say V is equal to minus Ri prime because passive sign convention is not satisfied. Okay? And when we reverse the direction of the current, the value acquires a minus sign. So I prime is minus I, and we recover our original relationship that V is equal to Ri. So you learned in college that Ohm's law is V equal to Ri. We are going to unlearn this relationship. We will no longer say V is equal to Ri. So what we will say is V equal to plus minus Ri. We will choose the plus sign when passive sign convention is satisfied, and we will choose the minus sign when passive sign convention is not satisfied. There are 2 important consequences of Ohm's law. The first one is when we connect an ideal wire between 2 terminals. Ideal wire is characterized by the condition that its resistance is 0. And when we connect 2 terminals through a zero resistance wire, that is called a short circuit. If you apply Ohm's law to this short circuit, we see that the voltage V is 0 because R is 0. So our general conclusion is that the voltage across a short circuit is always 0. The next consequence, we do not connect anything between the 2 nodes. If we do not connect anything, that is an infinite resistance. An infinite resistance is called an open circuit. If V is equal to Ri, then the current is voltage divided by resistance. So if we divide a finite voltage by infinite resistance, the current becomes 0. In a generalized way, we can state that the current through an open circuit is always 0. These are 2 important statements, and we will use these often to simplify our circuit analysis. Next, we go to KCL and KVL. But before we start discussing KCL and KVL, I will introduce 2 terms which are necessary to understand these laws. The 2 terms that I will discuss now are node and loop. What is a node? A node is a junction of two or more circuit elements. What is a loop? Loop is a closed path in a circuit formed without going through any circuit element more than once. Okay, let's look at a circuit and try to understand what a node or what a loop is. We have this circuit, and first we want to identify how many nodes are there in this circuit. Some nodes are obvious. For example, if we look here, the voltage source V1 and resistance R1 are connected. So this is a junction of two circuit elements. This is a node. If we look here, three circuit elements are connected: R1, R2 and R3. So this one is also a node. If we look at this junction, again three elements are connected: R3, R4 and current source I1. So we observe three nodes: 1, 2, 3. And at the bottom, this is a junction and this is a junction. So let's identify all these nodes and the junctions. 1, 2, 3 junctions form 3 nodes, and we have 2 more junctions at the bottom. Are these 2 junctions 2 different nodes? The answer is no. Why? Because if we look at this junction and this junction, the 2 junctions are connected through an ideal wire or through a short circuit. The voltage across a short circuit is 0. So although this and this junction looks different, they are at the same potential because the voltage between them is 0. Now this is an important part of understanding nodes. If we have multiple junctions in a circuit, all of which are at the same potential, they do not create different nodes, rather they belong to the same node. Actually, if we look at the circuit in more detail, you can see that a short circuit extends from the bottom of the voltage source V1 all the way to the right of the current source I1. So this entire short circuit is a single node, although it may look like that there are different nodes. So this entire part we will call one node. So how many nodes do we have in this circuit? 4. 1, 2, 3, and the bottom part is one single node. We will give each node a name: A, B, C and D. So this circuit contains 4 different nodes which we have named as A, B, C and D. Next we want to know how many loops are there. It is easy to identify the loops. A loop, we can travel in 2 possible directions. We can go clockwise or we can go counterclockwise. So remember that same loop can be traveled in 2 different directions. First, we look at clockwise travel. There are 3 loops which we can see obviously. This one, we start from A, go to B, go down through R2 to D and return to A. So this is one loop. The other loop is the middle one. We start from B, go to C, go down through R4 to D, go up to B through R2. This is another loop, and you can see that when we are defining these loops, we are not going through any circuit element more than once. And the third loop is this one. We start from C, go through the current source to D, then we go to C through R4, and that is the third loop. So we can show these 3 loops, 1, 2, 3, through these curved arrows. The question is there any other loop in this circuit? Of course. If we combine loop 1 and loop 2, we get a bigger loop: A, B, C, then D and A. This is a bigger loop. We can get another bigger loop by combining loop 2 and loop 3. B, C, go through the current source to D, return to B through R2. This is another bigger loop. So we identify two more bigger loops. Is there any other loop? Actually, there is one more. We can combine all these loops, all these three loops together. A, B, C, go through the current source to D and return to A through the voltage source. This combination of three loops is another loop. So we can show these loops with these arrows. The green one shows loops formed with two inner loops, and the yellow arrow shows the biggest loop formed with all these three loops. So we can see that there are in total 6 loops, although the internal loops, if we look at the smallest loops, there are 3. Okay. Now we are ready to discuss KCL and KVL. Kirchhoff's current law, or KCL, says the algebraic sum of all the currents leaving a node is equal to 0. I have written entering within parentheses. You can replace leaving by entering, but do not use both words at the same time. The statement we are looking at is without the bracket. The algebraic sum of all the currents leaving a node is equal to 0. Now, what does algebraic sum means? Algebraic sum means we add the currents including their magnitude and signs. Some currents may be positive, some currents may be negative. Now, how do I understand when a current is positive or negative? To understand that, we will follow a convention. At a node, there are two possible directions for a current. The current may be entering the node, or the current may be leaving the node. It doesn't matter which one you consider positive, but once you consider one positive, the other has to be treated as negative. To avoid confusion, we will stick to a single convention, which is we will treat current leaving a node as positive and current entering a node as negative. If you do the opposite, there is no harm, but you have to remain consistent. Now let's consider a circuit in which we have a node N. This N node is connected to 5 different circuit elements through 5 different wires. We have zoomed in at the node. So the rest of the circuit is not shown here. We are just showing our node N and 5 circuit elements which are connected through the wires. Only the wires are shown. Each wire is carrying a current. Either the current is entering the node or leaving the node. Let's say we arbitrarily choose the reference directions according to this diagram. I1 current is entering the node, I2, I3 are leaving the node, I4 is again entering the node, and I5 is leaving the node. So if we write the equation according to KCL, I1 is negative, I4 is negative because they are entering, the 3 other are positive, and this is the resulting equation from KCL. We can move the negative terms to the right hand side. And here we see that the left hand side represents some of the currents leaving the node, and the right of side represents the sum of the currents entering the node. So an alternate representation of KCL is that the sum of the currents leaving the node is equal to the sum of the currents entering the node. Now let's talk about KVL, or Kirchhoff's voltage law. This is similar to KCL but deals with voltages instead of currents. KVL says that the algebraic sum of all the voltage drops around a loop is equal to 0. Within parentheses we have rises, but let's ignore it for the moment. Now, what is the voltage drop or voltage rise? To understand that, let's look at this circuit element. We have a circuit element whose voltage is V. The reference polarity is such that plus is on the top and minus is on the bottom. Now we can travel through this circuit element in two possible ways. We can go downward or we can go upward. If we go downward, we face the plus first, minus second. That is, going downward, we are going from plus to minus. On the other hand, if we are going upward, we go from minus to plus. So going downward, when we go from plus to minus, this is called a voltage drop. In the downward direction, V is a voltage drop. And in the upward direction, V is a voltage rise. The two are opposite if one is positive, the other is negative. Again, it doesn't matter which one is positive and which one is negative. If you treat one as positive, the other has to be considered as negative. To avoid confusion, we will follow a unique convention. The convention says voltage drop is positive and voltage rise is negative. Okay. Now we consider a circuit with a loop. There is only one loop here. The circuit contains 5 elements, 1 through 5. We have assigned a voltage with each circuit element with arbitrary reference polarity. V1, V2, V3, V4, V5. According to KVL, the algebraic sum of all the voltage drops around this loop is 0. We can travel this loop in two possible ways, either in the clockwise direction or in the counterclockwise direction. For simplicity, we choose to go in the clockwise direction. So when we go clockwise, going across 1, this V1 is a rise, I go from minus to plus. When going across 2, V2 is a drop because I am going from plus to minus. Similarly, going from left to right, V3 is a drop. Going downward, V4 is a rise. And going from right to left, V5 is a drop. So V1 and V4 are negative because they are voltage drops. V2, V3, V5 are positive because they are voltage drops. So in the clockwise direction, we write minus V1 plus V2 plus V3 minus V4 plus V5 is 0. This is KVL. The algebraic sum of all the voltage drops around a loop is 0. We can move the negative quantities to the right hand side as before, and this is the equation that we get. Here we can say that sum of voltage drops in the loop is equal to sum of voltage rises in the loop. This is again an alternate representation of KVL. And this sentence tells us that if we had written the KVL by going in the counterclockwise direction, we would have obtained the same equation. The voltage, the sign of each voltage would have been opposite. Okay, now that we know Ohm's law, KCL and KVL, let us try to solve a problem. Here in this circuit, there are 4 circuit elements. We want to calculate the power of each one, P1, P2, P3, P4. If you notice carefully, you will see that this circuit is very similar to the circuit which we solved at the end of our last lecture. There are some differences. The major difference is the values of some of the circuit variables are missing. The current through this rectangle and this 2-volt source, the current is not shown. Similarly, the voltage across this 0.6 ohm resistance is not shown. The value of I1 is also not shown. In the last example, when we solved the problem, all the voltages and all the currents were shown, and we had to apply only this equation, that P equal to plus minus VI. But in this case, before we can apply P equal to plus minus VI, we have to find the values of the missing circuit variables. Okay, first we want to calculate I1. If we look at this loop, there are three voltages: 5 volt, 2 volt, and the voltage of the dependent source, which is 0.6 I1. Remember, the 0.6 I1 is not a current, it is a voltage. Out of these three voltages, values of two are known, only one is unknown. So if we apply KVL, we get -5, negative because it is a voltage rise, 2 volt is a drop, so positive, 0.6 I1 is also a drop, so positive. In this equation, only I1 is unknown. So with simple algebra, we find out that I1 is equal to 5 ampere. So this current is 5 ampere, this current is 3 ampere. Next, we want to know what is the current flowing through this branch, this rectangle and this 2 volt. We know that the current through both these elements are the same, but no current is shown. If we need to calculate a circuit variable which is not shown in the circuit, we have to assign the circuit variable ourselves. So we assign the current I2, and when assigning, we have given it a name and we have also given it a direction. Without the name and the direction, the current specification would have been incomplete. And that we have chosen the current from left to right, this is just our choice. We are free to choose the direction of the current. Okay, now let's look at this node. There are three branches with three currents. This branch current is I2, which is entering the node. This branch current is I1, which is leaving the node. And this current is 3 ampere, which is also leaving the node. So if I write KCL, current entering is negative, minus I2, current leaving is positive, so plus I1 plus 3 equal to 0. Again, I1 is 5 ampere, so we find out that I2 is 8 ampere. Now we know the voltage and current to calculate P1, we know the voltage and current to calculate P2, we know the voltage and current to calculate P3. We need to know the voltage of the 0.6 ohms resistance to calculate P4. So we assign a voltage across 0.6 ohms. Again, to assign a voltage, we have to give the value a name and we have to specify the reference polarity. Arbitrarily, I have chosen the plus sign to be on the top. 0.6 ohms is a resistance. In a resistance, we can apply Ohm's law. And the current through this resistance is I1. If you look at the directions, I1 and V1 satisfy passive sign convention. So V1 is plus I1R. I1 is 5 ampere, R is 0.6 volts. So V1 is calculated to be 3 volts. Okay. So we now have all the voltages and all the currents to calculate the four powers. P1 is, the current is I2, 8 ampere, and this voltage is 5 volts. So minus 5 I2 is minus 40 watts. Negative sign tells us that this power is supplied. For element 2, the voltage is 2 volt, the current is I2. I2 is 8 ampere. So 2 times 8 is plus 16 watt. Plus sign tells us that the power is absorbed. Similarly, for P3, the voltage is 0.6 I1, which is 3 volts, and the current is 3 ampere. So the power is plus 9 volts. Finally, P4, I1 and V1 satisfy passive sign convention. So plus V1 I1, V1 is 3 volt, I1 is 5 ampere. So the power is plus 15 watts. We have obtained the results. If you add all four powers, that is, if you calculate P1 plus P2 plus P3 plus P4, you will see that the sum is 0. Why? We had discussed that at the end of the last lecture. So this is all for this lecture. I will end here. Thank you.